Hello, we continue with electricity now. Before this, we looked at current, whole bunch of current stuff. Then we look at potential difference, EMF, internal resistance, a whole bunch of stuff. Now we're going to look at the third important part of electricity, resistance. Okay, it's not new, you've been looking at resistance already, but today very specifically, we're going to look at a couple of ideas. The first one is, how do you define resistance and the ohm, its unit? Then we're going to look at this kind of familiar equation, VIR. When can you use it, how to use it, why we can use it, all those kind of stuff. And then we're going to look at Ohm's law, which is created by someone. And that's it. All about resistance today. First things first. In case you are confused with resistance or you may see this kind of thing, join the resistance. The whole idea of resistance is, if you want to do something, something else is going to fight against you. When you want to move, air resistance try to stop you. When you want to flow in the electric pipe, when you are electricity, you want to flow in the current, there will also be resistance trying to oppose you. Like this poster here, when there's good force, there's evil force, there's resistance law. You want to do something, always got resistance. Okay, anyway. Yep, that's a side note. Anyway, back to resistance. Resistance, basically you can define it as the ratio of potential difference to current. What does that mean? Well, ratio, note the word, I highlight the word ratio because usually you see V equals to IR, then you say resistance, then resistance must be V over I lah. It's a ratio, not a gradient. So I cannot say change in V over change in I. No, that is for gradients. Later when you come to graphs, this will be an important point because if you have graph of V against I, then you want to find gradient? No. So it's just ratios. Okay, ratio. And the unit of resistance, we use ohm. Ohm is this symbol, omega. That's a symbol for, it's not symbol, the unit. So if a resistance of 16, you say 16 ohm. R equals to 16 ohm. Basically, it's the same thing lah. How do you define 1 ohm? 1 ohm is 1 volt per 1 ampere. So because V over I lor. So that's it lor. That's how you can define it. So if you have like a resistor in a circuit, remember this picture? Oh my goodness, there's more must-watch videos here that I'm going to add. Very, very good animations here. So if you have that resistor, you see that lumpy thing, right? That is a symbol for resistor. The other symbol is just a box. Or it can be the lumpy one. But when your chargers are trying to move, right, they will come across this bump here, then they're like, and they kind of find it hard to move. Let me show you the animation lah. I'll just show you the animation. So you see, right, this thing, the YouTube one, they're all moving, but then they bump up and down over here, so the current is slower already lor. That's the whole idea of resistance. Something is in your way, so you cannot move fast enough. Anyway, go watch out this whole video. Very informative. And it will definitely help you understand resistance better. But now the question is, how would you define resistance in an experiment? If I say, okay, I give you a bunch of wire, and now you have to define experiment. How would you find a resistance of, say, a piece of wire or a resistor? Let's go and look at one passage which basically talks about this experiment. Page 51. Here we go, the paper 2 question, page 51. ON12 P21. Classic. Let's start off with a definition kind of question. You can, for this one, let's do it together, so you can just do it as long with me. If you need more time, you just pause lah, or slow down. Perks of watching a video compared to a live class. Anyway, define electrical resistance. We just talked about that. It's a ratio. So some people may prefer to write a formula, but I'm just going to say it is the ratio of what over what. If you forget, remember V equals IR. Rearrange, R equals to V over I. And it's a ratio. Not dV dI, the gradient, nope. Not change in V over change in I, nope. So ratio of, you can say voltage or potential difference. I'm going to say potential difference. That's the formal CIE name. Potential difference over current. You can write this equation out lah in words, also can. You say ratio. So that one is, straight away you get a, wow, that's a very thick red pen. B1 mark. Then you come to the second part down there. A circuit is set up to measure the resistance of a metal wire. So here we're trying to measure resistance of metal wire. What metal wire? Anything, no? Could be a random piece of metal, could be copper, could be silver, could be iron, who knows? The potential difference across the wire and the current are to be measured. Oh, so you have to design the experiment. You need to think about what are the equipment that you need to use first. How to use? Think about it a bit. One. Well, the first hint is in any circuit, you probably need batteries on your list. So batteries like this kind of battery thing. Okay, so remember, okay, so we need a battery somehow to provide your power. If not, how are you going to power your thing? Okay, so you put battery lor. Battery. Then, what else do you need? Resistance of metal wire. So you need your metal wire. Okay, sure. So we need metal wire. But we have one problem. If I just connect, let's say I say this is my metal wire, right? I kind of treat it as a resistor. Metal wire. Okay. How are you going to change the current in the circuit? Because if you want to measure V over I, you need some way to change this and well, you need some way to change these values, V and I, so you have many different values of V and I. You need to draw a table, remember? How do you change the current of the V across this wire? Let's keep that in mind. So another thing you want to remember is you want to measure V across the wire, so you must connect a voltmeter. In experiments, they look something like this. Okay, these are multimeters that we use in the lab, but don't write multimeters in exams. Write voltmeter, so something like V. Voltmeter, connect across. You want to measure the potential drop across the metal wire. So from 2 points. We need to measure the current in the wire, the current I. Oh, okay. So we just find somewhere to put the ammeter lor, wherever you want to put it. Here is all in series, so why don't I just put it here? Let's put an ammeter right here, A. Okay. That's it. Oh, we still need the problem, how to change the current in the circuit. Here's what we can do. In labs, there's two things we can do. One thing is we use what we call the potentiometer or rheostat. You probably have seen this thing before. Okay. You can change the resistance of this thing by shifting this slider up and down. It's also called a variable resistor, okay? So, yep, this is rheostat. And we're going to use the rheostat to change the current in this circuit. For example, what if I add a rheostat right here on the left side? So I come down. Rheostat symbol is like a resistor, but with an arrow like that. The arrow basically means you can change now. So here I have a rheostat. Rheostat, aka potentiometer to vary the current in the circuit. Okay, because your current will be flowing, this I. And we want to change that so we get different values to draw on our table. If you're wondering, means need to add the potentiometer. There's a shortcut way, but I show you also lah. If you do power supply like that, means you connect to some special machine that will give you electricity. Then you can just straight away do like this. The wire, and then you measure voltage across the wire, and you add ammeter in series. Like that. Then maybe this one is a 12 volt supply. Also can lah, but make sure you know how to use the rheostat thing as well. So here you see there's 3 marks. Oh my. Am I blocking the 3 marks? Yes, 3 marks. Oh my. Where do the 3 marks come from? Well, if you check the mark scheme, you realize that the first mark comes from the metal wire in series with everything else. So first mark, wire in series with your battery or power source. Okay, that's correct. Second mark, forgot to say wire in series with your what was it called? Ammeter and your battery. Sorry, I forgot to mention ammeter. and battery. Because you also want to measure the current through the wire, so current is the same lah. Okay. Second one comes from your voltmeter, because you need to measure V. So voltmeter must be parallel to your wire. So voltmeter parallel. How to spell parallel? Parallel lah. Pardon my writing a bit. Third one comes from your rheostat or potentiometer in series with everything else. So current will flow through the rheostat before going to the wire. So that's the third mark. Okay. So that's the way we can use it to measure things like this. All right. Now, what are they asking us to do now? Okay, so you imagine you are trying to do this experiment. You set up the lab, everything. Then you collect data. Then you plot your data. And your data somehow looks something like this. Wow, not bad. Get a very nice straight line here. So here they say the readings for your PD, V, and your corresponding current is obtained. Okay, so these are all the readings for everything across that wire. Let me redraw it for you. So this is the wire, kind of like a resistor as well. It has some resistance. You have some current flowing through it, and you have a potential drop across the wire. And this everything is plotted out here in the graph. Explain how. Oh, this is chapter 2 stuff here. Uncertainty and systematic stuff. Okay, sure, let's do this too. Explain how the figures show that your reading got systematic uncertainty. How do you know in any graph in paper 2 or in paper 3 if there's a systematic uncertainty? Systematic means all your reading have this error, so all your data is shifted by a certain value. You can see that by this intercept here. Supposed to have no intercept one, right? Because R is, well, if this, you have V equals IR, right? And then you plot a graph of I against V. So I against V over R. So you're plotting this. There's no plus C or no plus something. So there should not be an intercept. This is the pattern of the straight line graph. Y equals to mx. Your m is 1 over r lah. Let me write it like that. 1 over r times your x. X-axis is v. So like that. So should not have intercept, but how come you got intercept here? Oh, so you got a systematic uncertainty there already. So you can say, because there is an intercept over there. Okay, let's do that. So we say intercept of 0.05 amps on graph. Supposed to be starting from 0 if you plot I against V. Okay. How do you know your reading got random uncertainty? Random means don't know lah. Suddenly you're doing one measurement, then it run a bit. You're doing another measurement, somebody sneeze, your measurement run a bit. So how do you know if there's random? You look at the data, they're kind of scattered. You have a best fit line, but you have a point up, down, down, up, down. So you can talk about the scatter in your data. So random uncertainties, you can see it as scatter of points about your best fit line. That's why we draw best fit line in the first place, to account for all this random uncertainty, random error. Okay, this one is 1 mark each, so B1, B1. Now comes the part where we have to actually calculate something. Use the data from figure 2 to determine R, resistance. Okay, so we look at this one. We need to find what is R. If you say, oh, can we draw triangle? We find the gradient. Wait. Technically, you could do that, but R is supposed to be ratio, so you don't need to draw triangle. You just choose a point. Now you need to choose a point, right? You need to find one that is very nicely passing through the corner. So I try to zoom in as big as I can to see. Which point shall I choose along the line? You just need to find one where it cuts a corner nicely. I like this one. This one looks good right here. You know, let me just use a highlighter. This point looks good. So that will give me 2.0 and 0.14. So I'm going to choose this value to calculate my ratio. Like that. Okay. Now I can zoom out. So you can choose a different point. Please do. As long as it's in the corner and it's a pretty decent one. Okay. Here there's one thing to remember. Interestingly, they say explain your working. Why is that? Never mind. Let's write down what points I have first. So I chose for my V 2 volts. And for my I chose 0.14 amps. But before you calculate resistance, you need to consider this systematic uncertainty that we have here. There's a zero error. When your V is 0, how come got current one? Okay, so this is a positive zero error because it's positive. So we need to get rid of that. So, since you want to mention that, since I has zero error or systematic uncertainty, you can say that positive 0.05. So you want to use I is 0.14 minus out the zero error. Because you need to shift down your value ma. So 0.14 minus 0.05. So we'll use a current of 0.09 instead. Okay, that's because 0.15 here, but you need to shift all your data down a bit because of that intercept that's not supposed to be there. Now we can only can calculate your R. Ratio is V over I. So your V, 2 volts. I, make sure it's in ampere, not milliamp, 0.09. Calculate. If you are using different values, also can. Should get roughly about 22 ohms. So round off, if you use 2SF, will be 22 ohms in this case. 3 months, man. Where does this come from? First one comes from you explaining this zero error thingy. Why you minus stuff. Second one is coming from you using your values of V and I, which is a corrected value for zero error. This is a second mark. I think it's a C1. Let me double check. C1. Oh, B1, C1, A1. Okay, correction is B1. There we go. And the final one is A1 accuracy mark for this. Pretty nifty. This is the experiment for how you can determine the resistance of pretty much all kinds of stuff. Make sure you have ammeter, voltmeter, and then you change your V, and then you see what the I come out. This will be very important in the next video too, by the way. So this one we are changing. I'm going to leave part C to you to try out because it's something to do with uncertainty stuff. Go try it out and review it. But I'm continue here with the resistance part of today's lesson. To drive home the point about ratios, let's look at this question on page 23 about graph resistance. Okay, this is ON14 P11 page 23 on the bottom left. Now I want you to try this one out. It's not too long, it's kind of short, but choose your answer. It's okay if you get it wrong as long as you know that, oh, I got this wrong last time. It's quite helpful to do that. And let's see. What did you choose for this? If you have not pause it, choose first. Read it, what we're trying to do here. Okay, we have a graph, current against voltage, like what we did just now in that experiment, through a conducting liquid. Ooh, that's so weird. No wonder it's curvy one. Okay, so that means your resistance is changing. Because previously, if you had a straight line, all the ratio here will be the same. But here, it's kind of changing. So what would you choose? Warning, reminder. R is not your gradient here. Gradient is the steepness of slope lah, so the slope. So maybe if you think of too much maths already, you say, oh, this one B very steep. So the answer at B lah. No, we want to think about ratios. Here, R smallest resistance. Okay, resistance is V over I, the ratio. And you want this to be the smallest. Means V divided by I must be smallest. What does that mean? Okay. Let's look at D first. For D, this height is your value of I. Your value of V is very big. So means V divided by I is very big. So this is R is large. So nope, not R. So how would you decide between A, B, and C then? Let's look at A first. A, your I current is a little bit small value. V is pretty big. Okay, compared to this one, this one, the value is a little different. V over I. Okay. This one, the resistance is a little smaller because V is a little more same size as I. Then we go to C. C, among A, B, and C will probably give you the smallest resistance because V divided by I is quite small. This one, V divided by I is very big, the ratio. We're looking at ratios only. See, V very long, I very short. Here, V almost the same length as I. Okay, so the answer is C. Okay, so we'll choose here C in this case. Zoop. Reminder, write a star on your paper so you can know for sure. Now, before we go on to a few more questions that I've prepared for you, I want to tell you about Ohm's law. There's also some space in the handout for you to take notes on this. So previously we defined resistance. Now we talk about Ohm's law. Okay, Ohm, there's this guy called Ohm. He's a German. His full name is Georg Simon Ohm. And this guy is quite a genius, okay? He played with water and then he thought about electricity. So he's like, oh, water pour here, water pour there. He said, oh, electricity actually is like water in a pipe. High potential to low potential, it flow. Flow here, flow there, flow here, flow there. So what he discovered is not actually a law. Ohm's law is not technically a law. It's more like an observation, a rule on how electricity behaves. He just like, oh, this is how it behaves. So what he discovered is, what we looked at just now, kind of. Current is proportional to the potential difference across it. Think about that for a moment. Okay, what does that mean? So if you have a resistor or some light bulb, whatever it is, you have a current and you have a potential difference across it, V. There will be a relationship between these two. Okay, so current proportional to the potential difference. But there is one condition for Ohm's law. Only for Ohm's law, for Ohm's law to be true, physical condition must be constant. So the temperature of your component must not change. Because you want resistance to be constant. Only for Ohm's law. Like just now you see resistors, right? The weird shape graph. That one resistance is changing, but only for Ohm's law, resistance must be constant. So if you have a graph of say I over V, current against voltage, if it's a straight line, then yes, you can say this resistor obeys Ohm's law. Okay, Ohm's law, two ideas. First one, I is proportional to V. Check. Yes, correct, straight line. Physical remains constant. So is it a straight line? Yes, it's a straight line. So straight line. Two conditions to obey Ohm's law. Not everything obeys Ohm's law, by the way. Resistors usually will obey Ohm's law. So we'll call this ohmic resistor. But a lot of other electrical components actually don't obey Ohm's law. They will have very weird graphs. And the next video will talk about all those weird graphs. But now we're going to look at things that obey Ohm's law first, okay? And if the exam ever asks you, so you obey or not obey, how you know? You do the ratio. R must be constant, right? So you choose one value here. You find your ratio. R1 will be V1 over I1. You calculate, what is it? Then you choose another point, must have 2 points. Then you find a second resistance value, V2 over I2. Then it's R1 and R2. If they are the same value, means your resistance is constant, and therefore this component obey Ohm's law. Okay, it's the same thing with Hooke's law if you have seen before some of these questions. But yeah, that's how you can talk about Ohm's law. The only thing is, what is constant, what is proportional. That's why you must keep in mind. This is how it's different from the resistance thing that we've talked about in the previous slides. Now let's look at some questions to apply this idea. The first question of today is on page 75, a paper 2 question. For this one, don't do the whole thing yet, but take some time to do until the part B here at the bottom, just the left side page. You can skip the ratio part. You can save it for later and try it out after class to practice. Okay, how many marks is this? 1, 2, 3, 4, 5. 5 marks. So how long should you take for this? Roughly 6.5 minutes. 5 times 1.25. So take 7 minutes to try this one out, see how to do, and come back and check through together. Okay, first one, define the ohm. Ohm is the unit. So ohm, you have to remember, oh, R is V over I. Check and see, V equals to IR, so R is V over I. So you can say ohm is volt per ampere. That's it. Like most of paper 2 questions, you start off with definition. So make sure you memorize these things, make a list of them, and so you can memorize, can review lah. If not, you have no idea what definitions they are. You just blur, go and exam. I think it's this definition. Yeah, go and memorize it. Then we come to a circuit. Ooh, there's some stuff in series, some stuff in parallel here. A cell of EMF 1.5 volts, negligible internal resistance. Aha. No internal resistance. So don't need to worry about that. It's just 1.5. Good. Connected in series to 3 resistors, A, B, C. Each one have resistance and parallel. Some are in series and some series, some parallel. Calculate the current in the circuit. The current in the circuit here refers to this one, I. When you come to this part here, yeah, the current will split, but we're not going to worry about that. Then they'll join back and then become I again. I, and then go back. So this I is what we're looking for. How do you know how much the current will split? Well, we'll save that for chapter 20. There are very neat tricks you can do to calculate how much current split. But what we can do now is combine that parallel section. This thing here is called the parallel section. 2 resistors in parallel. So to combine resistors in parallel, here's the rule for it. A good refresher of IG and SPM. If you have parallel resistors, the total resistance here will be 1 over RA plus 1 over RB. But it's 1 over, okay? So when you want the resistance, you have to flip the whole thing. So 1 over RA plus 1 over RB, negative 1, or 1 over the whole thing. This is how we can combine to find your total resistance for this section. Okay, so let's do that. V equals to IR. So if you want to find R, what do? R is V over I. If I want to do all this in one step, can? Can. You treat this R as total resistance of the whole circuit, including the resistor C. So potential drop across this whole thing is same as the one as the battery, 1.5 volts. So 1.5. Why I find R? Sorry, wrong part. I want to find current. So V over R. R, total resistance. You need to do a few things. Firstly, you need to combine this A and B. So 1 over RA, 1 over RB. Let's do it in 2 steps here, shall we? So if I combine these two, RAB combined will be 1 over 6 plus 1 over 3, negative 1. What is that? And 1 divided, 2. 2 ohm. So that means I can redraw my whole circuit into something simpler like this. So this one is RAB combined already, become 2 ohm. This one is 4 ohm. Yeah, now it becomes series, you can just add lah. Yep, now you can just add it. So here will just be 2 plus 4 ohm. This is a very helpful skill to deal with parallel things later when you come to more complicated circuits. Simplify first, all the parallel one you combine into something easier, like this one here. Combine all the parallel into one effective resistor. Okay, got current, calculate. 1.5 over 6. Current is quite small. Well, this is normal for small circuits with battery, 0.25 amps. So 0.25. 3 marks. Where does this come from? Well, you can guess one comes from final answer. Where do the other 2 marks come from? One comes from your working of V equals to IR rearrange and either here or here lah. One more mark actually comes from this thing. C1 mark. How to deal with parallel resistor. You have the 1 over 6 plus 1 over 3, those kind of stuff. So that's 3 marks in total for this one. Then they ask you, what is the current in resistor B? Where is B? Oh, here, B. Oh, this one, they're looking for current going through B. So I'm going to name it IB. Here you are thinking like, oh, now we have to find the current split already. How to do? Is there a formula to see how far the current will split? Yes. Chapter 20, pause. Let's use another trick. If I can find what is the potential drop across this part, I can find what's my current. So by potential drop, I mean from here to here, there is a potential drop VB, which is also the same as VA, by the way. Can I find what that VB is? How would I do that? I have another question for you. If I can find VC, then I know VB plus VC must equal to 1.5 volts because that's what the battery supplied in the beginning. That's an idea. Let's try to find VC since we know the current is 0.25 amps now. So here, let me rename. 0.25 amps is flowing through C. And you know it's a resistance of 4, so you can find VC. Okay, ons. Let's try that. So I'm going to find what is VC first. VC will be I times R. Current is 0.25. Actually, let me write out one more line. VC is IC times RC. R is the resistance that's given to us, 4 ohm. So that means VC is 1 volt potential drop. So this one dropped by 1 volt. So if here drop by 1 volt means this side must drop by how much? 1.5 minus 1, 0.5 volts. Okay, sum of potential drop is the same as what your battery give. So we know VB is 0.5 volts already. Now we can calculate things. So we know VB equals to IB equals to RB. We want to find, what was it, IB, right? So VB over RB lor. So the VB we found is already 0.5 volts. And that one divided by R, what is RB? 3 ohm. 3. So what do we get here? 0.5 divided by 3. Wow, 0.166666666666667 amps. In the final answer, you can write 2 or 3 SF. Let's go with 2. I'll go with 2 now. You can write 3. So 0.117. Never mind, I'll do 3 lah. 167. Okay. A reminder, where does this come from? This is because VB plus VC equals our battery potential, which is 1.5 volts. And VC we just found is 1 volt. 1. That's how we got a 0.5 there lor. This one only 1 mark do all this stuff. Okay, because Eventually, they'll expect you to know, oh, automatically here, no need to write out the working. But your 1 mark just comes from your final answer, 0.167. The rest is kind of me writing it out step by step so you can see where we get to 0.167. Okay? So that's this part on the battery resistor, how to think about parallel and series. Series, you just add. All the resistors add up. Parallel, you have to add them in a very special way. Add 1 over, 1 over, 1 over, like that. Okay? So yeah, take time to complete the question. It's also in the practice question list, especially part D. I think you skip part C now. Part D. Go try it out and see how you can solve that one. Okay, let's go and look at some objective questions that are kind of strange. The first one is on page 24. Wow, look at this. It's pretty common to see really weird circuits like this. You're like, this is nothing like what we've seen before, miss. You can still do it. You just need to adjust a bit. Let's see what is this about first. Extension LED is connect electrical supply. Okay, so we know electrical supply to a heater. This is the heater on the right side. Voltmeter measure the PD across the heater as 216 volts. Let me label that. 216 volts. Okay. And an ammeter measures the current as 7.7 amps. What is the total resistance of the extension LED? Total resistance so means there's actually two things here lah. There's a R here and there's a R here. So well, R1, R2 lah. Both you can consider the same because they are part of the same extension LED. But how would you find the resistance here? Some of you may be able to do this right away while looking at it, but for most of us, we'll be like, how to use Ohm's law here? I mean, so complicated. Here's the number one tip for circuits. Listen closely. When your circuit looks scary, redraw it into something you know, lor. Okay, so let's practice redrawing, and then I'll let you solve it up. Okay, so first things first. Let's put the power supply on the left. This is 240 volts, potential difference across both ends. Then I do my classic box circuit law. Come here, got first resistor. Go down to the heater. And then go to a second resistor. And then go back. Is it the same thing? Check and see. It is the same thing. It's just that literally the same thing, but now redraw in a format or a picture that you can recognize and solve because you are used to boxes. So, okay, practice redrawing. What do we have here? We have current measured flowing through is 7.7. This one have resistance, don't know what is it lah. Then your heater, oh yes, we have a potential difference of 216. So the voltmeter here, I put it in outside lah, is 216 volts. How do you start? If we knew, we want to find R. If we knew what the potential drop is across either one of the resistors, then we can find your R lah, right? Is there a way to find it? Yes, here's the trick. If your original battery got 240 volts, come to the heater got 216, means the voltage drop has to happen on these two R here. Okay, let me repeat. If your voltage is 240 here, potential difference, here there's a drop of 216, means your R1 and R2 must have a drop of 240 minus 216, which is 24 volts. So there's a total of 24 volts drop across these two resistors. So we can say here drop 12, here drop 12 volts. So you start off here, your current flow, drop 12, come here, drop 216, come here, drop 12, becomes 0, and then go back to battery. Okay, so there are multiple ways to do this. You can do total resistance, or you find one resistor and then multiply. But let's do total resistance. How about that? So we know the total resistance, because of the resistance there's a drop of 24 volts. Power loss. So V is for total. IR Total drop, we know, is 24 volts. Current, given to us, 7.7. Resistance, we're trying to find. So, 2.4 divided by 7.7 is 0.3116 volt. 2.4 pula, 24. Sorry, press wrong. I said, wow, that's a very small resistance. 3.11. 116 ohm. My head is blocking the ohm. 3.116 ohm, so you look. 3.1. Wow, this one very tricky. They put 31. So if you type wrong decimal like me, then wrong already. So here, 3.1. Moral of the story, circuits may look complicated, but redraw or simplify whenever you can. Use something that you can recognize. Okay, let's look at one more question about graphs. This one is kind of a circuit interpretation kind of question. I want you to pause this one, try it out first, see what you guess. It's quite, well, it couldn't be confusing, but you just try choose something first and we'll come together and we'll see how to think of these graphs. Voltmeter reading, current, all this stuff. Wow. Okay, 12 volt battery with emitter, 2 ohm fixed resistor, variable resistor. Oh, so this one can change one. It is like the experiment we did just now to determine resistance of a wire. Okay. So what is changing now? The resistance of the variable resistor is changed from maximum to 0. So they are taking this one, they adjust from maximum 10 ohm to 0. They change on, they take the knob, or you know this thing. They move it from maximum all the way until 0. Okay, then they measure all the things to see. Which graph shows the variation of current? Current is on the x-axis with the voltmeter reading. So you see, you have to think about how they change. Okay, so I'm going to write out step by step how we can think about this. So firstly, when your resistance of P is it increasing or decreasing? Decreasing resistance of P. So when the decreasing resistance of P means decrease, no space. Decrease, then your total circuit resistance is decreasing. Okay, the whole circuit resistance is decreasing. And that means your current in the system, current of circuit, is increasing. So this I here is getting bigger and bigger. I flow through everything, come back. I is increasing. Okay. And let's look at Q first. So current increase. VQ equals to IQ, the current flowing through I, times RQ. Now this one on the right is fixed. Just 2 ohms fixed already. So this is locked in. That means if your current is increasing, okay, that means your V is also increasing. Therefore, if you want to plot a graph for Q, for V over I increase, V increase, so proportional, like that. And this is for Q. So from this first part, you can go through the answers and see which one match the Q. So you look and see, Q increase, Q increase, Q increase. Q decrease. So this one wrong already. Bam. So this is out. Then we are left with P. What does P do? Oh my goodness. Okay, so let's look through P. Let's go through the same idea for P, step by step. So first things, we know previously here, we already know, right? R decrease, total, R increase. Okay, let me just skip to number 2. So the current in the circuit is increasing. So if I want to look at P, VP equals to IP, RP. Oh, I have a problem here because there's too many things changing. How? Because your RP is decreasing at some rate, I don't know. Your I is also increasing. or increasing. But then your V, how is it going to change? We don't know. Previously, we can know for sure because this one is constant. But now, there's too many things changing. Your VP will also change. So it's like, is it going to increase or decrease? We don't know for sure. So how are we going to solve that? For this, we'll need one more final fact. Here. Okay. We have trouble trying to use Ohm's law to understand this, but we can use another idea that we know. We know that this potential drop is plus this potential drop equals to 12 volts. So Vp plus Vq is 12 volts. That might be a useful piece of information. Vp plus Vq is 12. From the before, we know Vq is increasing. Here. So, if Vq is increasing, 12 volts is constant, 12 volts EMF. So that means our Vp has to increase so that it still equals to 12. So to relate current and Vp, you can say therefore, when your current increase through P, this is for the potentiometer, then your Vp actually is decreasing. Means if you draw a graph of V against I for P, I increase, V decrease, so something like this. I getting bigger, then your V will go down. This is for P. So now you have to look at which P graph is going down. There's only left D already. So D is the answer for this kind of graph. Wow, there. This one has many trains of thought. This is one of the trickier ones that you kind of have to really think through it carefully. So if you kind of felt like you were stuck there, not sure what just happened, it's okay. Go through it again, the reasoning. Make sure you kind of understand the reasoning that I wrote on the right side for both, this is for Q and for P. Okay, go through step by step the reasoning, why it's increased, why we cannot use Ohm's law for P because too many things changing. Okay, so that's all, most of the questions I want to show you for this part. If you want to know more, actually no, I say compulsory. Go and learn more about how you can increase current in the circuit. How does that relate to resistance? This kind of an extra homework for you. You will benefit from it. Trust me. So I want you to think about 3 ways how you can increase the current in the circuit by playing with resistance. How? What do you put in your circuit? How do you change the circuit? How would you draw a circuit? Well, the basic one is like this law R. Just now we really look at some. How will you change the current in the circuit? Because this one R is fixed. Okay, so list out 3 ways, then go to the video. Oh, this beautiful video. Go watch it. The link is also posted down in the description below of this video. So go to the video, confirm the 3 facts that they talk about. That will help you in tackling all kinds of problems, and also when you try to do labs, because you like, oh yeah, I know this one. Okay, so that's all for this one about resistance. Next up, we're going to look at more of those IV graphs, the ones where they do not obey Ohm's law, where they're all kind of curvy stuff. So I'll see you in the next video.